This is a single piece of cargo. It weighs more than 400 tons. It is wider than the track it sits on. It has millimeters of clearance on either side as it passes through towns, under bridges, and around curves designed for trains a fraction of its size. This is a high and wide load, and BNSF moves objects like this across America regularly, including components for entire power stations, nuclear reactors, and wind farms. The question everyone asks the first time they see one is simple. How does that even fit on a train? Standard trains are built for a highly rigid world. In North America, the invisible box that almost every piece of regular cargo must fit inside is defined by the loading gauge. This absolute spatial envelope restricts standard loads to a maximum of 6.4 meters tall and 3.2 meters wide. Railroads like BNSF and Union Pacific move millions of tons of freight daily, but anything exceeding these parameters cannot simply be thrown onto a standard flat car. If you try to transport a 400-ton power transformer, a massive refinery vessel, or a wind turbine blade stretching over 80 meters long on ordinary equipment, the laws of physics and infrastructure quickly intervene. A standard railcar would buckle under the concentrated weight. A tall load would strike overhead bridges. A wide load would scrape against passing trains, signal poles, or tunnel walls. The issue is more than extreme mass. It is a problem of shape, center of gravity, and length. A wind blade over 80 meters long cannot clear a curve on a normal flat car because its body would swing out dangerously wide, clipping everything in its path. A reactor pressure vessel weighing over 500 tons would shatter the wheel axles of normal rolling stock. Highways are not an option. These components are far too heavy and bulky for asphalt roads, which would crack under the pressure, and low-hanging highway overpasses make road transit physically impossible. To move the heavy infrastructure that keeps the electrical grid alive and the lights on, the railroads must bypass almost every conventional rule of modern transportation. They have to engineer a completely custom path forward. To bypass these physical limits, railroads deploy a mechanical anomaly, the Schnabel railcar. Instead of placing a massive load onto a car, engineers make the load part of the car. A standard flat car carries cargo on a flat deck. A Schnabel car has no deck. Instead, the vehicle is split into two separate halves. Each half consists of a massive steel arm resting on a series of wheel bogie assemblies. When a giant component, like a power station generator or a nuclear reactor vessel, is prepared for transport, specialized rigging crews bolt and weld the cargo directly to these two arms. The cargo itself becomes the structural bridge connecting the front and rear halves of the train. It literally holds the rail car together. The largest of these vehicles in North America is WECX 800. This 36-axle machine can support a cargo weight of over 1.7 million pounds, nearly 800 metric tons. Fully loaded, the entire assembly stretches 345 feet long, spanning more than the length of a football field. By suspending the cargo between the wheel sets rather than stacking it on top of a platform, engineers dramatically lower the center of gravity. In some configurations, the heaviest part of the load actually hangs below the top of the rails, riding just inches above the track bed. This low center of gravity provides stability, preventing a 400-ton load from tipping the train on curves. But lowering the load solves only half the problem. As the train moves, hydraulic systems on the Schnabel car allow operators to physically shift the cargo. If the train approaches a rock wall or a signal post, the rigging crew can slide the entire load up to 40 inches left or right, or lift it nearly 4 feet vertically. In the tightest sections of the route, the the clearance between the cargo and concrete bridge supports can shrink to under 100 millimeters, less than 4 inches. In these moments, the line between a successful move and a catastrophic collision is managed centimeter by centimeter by specialized ground crews. Before a single wheel turns, an oversized rail shipment exists only as a theoretical exercise. Months before departure, BNSF clearance engineers must verify every single meter of the proposed corridor, looking for any physical barrier that could halt a million-pound load. This is not a matter of checking a few notorious bottlenecks. Teams deploy specialized track inspection vehicles equipped with high-precision laser scanners, transforming real-world infrastructure into dense, three-dimensional digital models. They scan bridges, tunnels, signal gantries, platform edges, and overhead utility lines with millimeter accuracy. BNSF's internal clearance department manages this complex workflow, coordinating with regional track supervisors to guarantee that the digital scan matches the actual track conditions. Track environments shift. A maintenance crew packing new ballast under the ties can raise the rails by a few centimeters, unknowingly erasing the vertical safety margin under an overpass. Within the completed digital replica, routing software runs a simulated train through the virtual corridor. The margin for error is non-existent. A bridge abutment or a rock face protruding just 5 centimeters too far into the clearance envelope instantly invalidates the path. Because a train cannot steer around an obstacle, a single localized conflict forces engineers to draft an entirely new route. In the sprawling rail network, bypassing one tight tunnel can divert the train onto alternative subdivisions, adding hundreds of extra kilometers to the transit and weeks of planning. Once the physical move begins, the train operates within a strict speed band of 15 to 25 miles per hour. At these speeds, a trip that normal freight completes in hours stretches into a multi-day operation. The extreme physical length of the cargo introduces the hazard of curve overhang. While a massive load easily clears straight track, bends in the rails force the center of the cargo to swing inward while the ends project outward. This sweeping motion creates a wide footprint that can foul adjacent tracks and strike nearby structures. To manage this danger, a support network of track personnel and escort vehicles surrounds the train, monitoring clearances meter by meter. Ground crews inspect tight spots on foot ahead of the locomotive, communicating constantly with the engineer. When night falls, the train does not continue. The crew parks the multi-million-dollar load in pre-selected, secure sidings under the watchful eyes of guards. Every mile is a slow, highly coordinated effort. A single high-wide shipment can cost hundreds of thousands of dollars. This staggering bill covers specialized car leasing, extensive route surveys, round-the-clock escort personnel, and the massive financial impact of disrupting a scheduled freight network. Yet, railroads run these moves because the alternatives are far worse. Moving a megaload by highway often demands disassembling overhead bridges, lifting utility lines, and shutting down multi-lane freeways, a logistical nightmare that can easily push road transport costs past $1 million. Shippers accept the slow speeds and high costs of rail because BNSF can temporarily suspend ordinary freight logic. By making a rolling, one-time exception to normal operations, the railroad allows these giant components to move at all, keeping the nation's energy grid alive. Today, as our energy demands grow, these impossible moves remain the lifeblood of our infrastructure. The rails don't just transport cargo, they literally keep the nation's lights on. What engineering marvel should we deconstruct next? Let us know in the comments.